Hi everyone. This video will cover the missing data and power lecture examples using R at RStudio and Lavon. This accompanies lecture 5 for PSYC 7505. So the first thing we'll do is we'll load the Lavon, SEMplot, SEM tools, Amelia, and SimSem packages. That's a new warning. I'm not sure what that is, but we'll see if it causes any issues. And if it does, I'll start recording again. We're going to read in our data. Our data are, there are going to be several versions called lec5.parcel. So this is the parcel data that we've seen before. It's the same stuff we've seen before, just we'll see it again. So as a summary, there are 12 items, 12 indicators, 6 indicators of positive affect, great, cheerful, happy, good, glad, and super, 6 indicators of negative affect, sad, down, unhappy, blue, bad, and terrible. If we want, we could look at the covariance matrix of all of these. To make it a little prettier, we could round that covariance matrix. We can see, oops, one more time. We can see the covariances amongst all the items here. We can see that the positive affect items, great, cheerful, happy, good, glad, and super, tend to have positive covariances. The negative affect items all have positive covariances with each other, and between the two, there's negative covariances. So we can fit our CFA to our unparceled complete data. So just here we go. Positive affect has loadings on great, cheerful, happy, good, glad, and super. Negative affect has has factor loadings for sad, down, unhappy, blue, bad, and terrible. We're going to use a fixed factor method of identification. Positive and negative affect fixed to 1, and their covariance is in the model as well. These are just here for completeness. As a reminder, Lavon defaults will include these. So we'll fit the model using the CFA command. We say CFA, again, this is complete data. There are no missing data here. Call this DAT2. And we can look at our results. And these results are the same thing we've seen before. We've seen these data a bunch. We have 759 observations. We have a significant chi-square, but again, we're not going to worry about that because we know the null hypothesis is false. CFI and TLI are quite good, 0.977 and 0.971. RMSEA is good, 0.056, with a 90% confidence interval from 0.048 to 0.066. SRMR is 0.043. Those are all really good. And here we have our factor loadings we can investigate. We have the covariance between positive and negative affect. It's negative 0.29. Standard error is 0.037. The p-value is 0.000, and it's not actually 0, but it's very small. And our variance is here. And if we wanted to see a picture of this, we could use SEM paths. We can see here's a picture of what our model looks like. So now we're going to read in data. It's called, the data available is called lec5parcel.mcar.csv. These data have about 20% missing data that's missing completely at random. I put the data in on purpose just as an example. So one thing to note, missing data, if we look at the data, if we just look at the first 6 rows, missing data in R is noted as NA. So missing data in R is an NA. Anywhere there's an NA, that means there's missing data. If we look at a summary of the data, what we see is that there are, for every variable, it gives us the number of missing data points. So cheerful has 153 missing observations, happy 148. We can see throughout great, we have complete data on. To get a covariance matrix of the observations, if we do this, the first thing you'll note is there's all these NAs. The reason for this is we have to be a little bit careful with the default behavior with missing data in R and check what that is. So if we go to the covariance help page, what we can see is cove, there's this x, y equals null, use everything method equals. Pearson, what does use everything mean? We want to check that. So use optional character string giving a method for computing covariances in the presence of missing data. It should either be everything, all observations, complete observations, NA or complete, or pairwise. And down here it says if use is everything, NAs will propagate. So anything will be NA whenever there is missing data. So if instead we say use complete obs, this will do listwise deletion. So use complete obs, this gives us our covariance matrix based on listwise deletion. We get that right here. Now, so we can fit our model. The model syntax is exactly the same. as above. I've just got it down here for completeness. And if we fit our model now to this data, to the data with, by default, if we don't change anything else, so we just fit it to the data with missing data, Lavon will use listwise deletion. And so what happens when we look at a summary of our results? Oops. When we go up here at the top, the first thing is now when there's missing data under number of observations, there are two values. There is used and total. Total are the number of rows in your data set. Used are the number used for your model. So in this case, with listwise deletion, only 20% of the data are missing, but we've lost over 700 individuals. We've gone from 759 to 55. These data are based on 55 individuals. We can see in this case, model fit is worse. The CFI and TLI are a little bit worse. RMSEA is much worse with a really wide confidence interval from 0.039 to 0.132. SRM has gotten worse. This is a really small sample to be fitting this to. I wouldn't trust any of these results. Our standard error, which gives us information about power in this case, is 0.126. Remember, with complete data, it was 0.037. So there are really pretty massive changes here compared to what we saw, partially because we've lost data on 700 out of 750 individuals. We've lost data on most of our sample. So instead, we might use pairwise deletion. So here, if we use the cov function and we say pairwise complete observations, it will give us, we can get a covariance matrix, so cov pair. This is a covariance matrix based on pairwise deletion. So we fit that same model, but now instead of using specifying data, we specify a sample covariance matrix using pairwise deletion and the sample number of observations. So here I have 759, and that's probably not right because that's pretending, that's essentially lying. That's pretending we have more data than we have, that we have 759 complete observations. So I could run this. The model runs. There's nothing that will stop you from doing this except the knowledge that it's wrong. Let me try it one more time. And when we look at this, we can see this model fits pretty well, fit 0.96, 0.95 for CFI and TLI, 0.076 for RMSEA. Fit is pretty good. The standard errors, 0.036, are very small, but again, this is basing it on more data than we have. We don't have that much data. So, maybe instead we'd say, well, 20% missing, we'll say 600 is a more reasonable number of observations for our sample. Well, if we do that, that again affects our estimate of power. Our standard error now, our standard error is 0.041. We've lost a little bit of power. And again, this shouldn't be biased with MCAR like we're seeing here, but it will also be biased under MAR. Finally, we can use FIML. So to use FIML, full information maximum likelihood, we specify our CFA command. We have our data set with missing data, and we add this missing equals ML. This will use FIML estimation. Now, FIML is a little more computationally intensive. It takes a minute to fit. And then when we look at our results, so when we look at our results now, what we see up here at the top is it gives us the number of observations and the number of missing patterns, because FIML completes a likelihood for each different missingness pattern. So that's reported here. CFI and TLI are very similar to what we saw before, both about 0.97. RMSEA is the same, 0.047, very close to what we saw before with a similar confidence interval. So is SRMR. And we end up with, in general, really similar results. Now, our standard errors for the covariance is 0.038 instead of 0.037. So we end up with really similar results. These next bits, I'm not going to go through all of them. Compare the results of the complete data to FIML, and they're very, very similar. We could do the same thing with MAR missingness. So we're going to read in lec5 parcel.mar. In this case, it's missingness as a function of the variable great. So again, if we look at our data, we can see there's missingness on all the variables except great. Great is our auxiliary variable. We can fit our model with listwise deletion. Now in this case, just based on missingness patterns, what we're going to see is, now we use more data. This is just based on the missingness patterns. Now we have 373 out of 759 people. We've still lost about half the people in our sample, which is, a pretty meaningful thing. We've lost over half the people in our sample. Again, model fit is a little more accurate, again, because we have more people. but we start to see bias here. So this covariance is biased because this is MAR missing. Now our parameter estimates are incorrect. It should be about 0.29 and now it's 0.34. Standard errors are also larger. It's 0.052 still. We're still losing power. So we've got both bias and a loss of power here with listwise deletion, which is bad. We could do the same thing with the compute a covariance matrix based on pairwise deletion. Fit this model, the pairwise deletion model. And in this case, with the pairwise deletion model, again, we don't know what sample size to use. I just picked 600 at random. Model fit's a little bit worse. RMSEA is worse. Our estimate here actually just happens to be pretty close. Often, remember, with pairwise deletion, you'll also get biased results. Standard error is larger, again, because we don't know what sample size to use. Finally, we can fit this model with FIML. We say missing equals. You can either say missing equals ML or missing equals FIML. They're equivalent things. Both will work. I have this one in here just as an example. When that runs, we will look at the results. So these results now, again, 759 people, 349 missing mispatterns. Again, model fit is very similar, 0.98, 0.98 for CFI TLI. RMSEA is very similar to what we saw before with our other two examples. So is SRMR. Our estimate of the covariance, 0.29, is pretty much spot on. The standard error, again, 0.038. They're very, very similar to what we saw before. And if you want to check that, the model with no missing data is right here. A couple of other examples. So here's one where I'm just going to change this a little bit, where we're going to use an auxiliary variable. So we're going to say, okay, we're not going to use great in the model. We're going to use great as an auxiliary variable. We're going to pretend we have a variable that's not part of the model, but that is related to missingness. So here I have good, cheerful, happy, glad, and super as indicators of positive affect, sad, down, unhappy, blue, bad, and terrible as indicators of negative affect. And so I can use the CFA.auxiliary function. This is from the SEM tools package. We specify our model, our data. In this case, it's our data with MAR missingness. The name of any auxiliary variable. So here, great, the name of a variable. So I included and other Lavon options. And if we do this, because this isn't truly an auxiliary variable, we're going to get some warnings. Once it fits, it takes a little while to fit because of these warnings. And we get this warning about observed variables, not positive definite. Again, this is more a function of the fact that great should really be an indicator of positive affect. We're using it inappropriately. So what we end up with here, if we look at a summary, oh, I should add, you should get fit measures. Fit. I won't ask for standardized parameter estimates here, but you can get those as well. Everything pops out the same way. We get information about our estimation, CFI TLI, RMSEA, all of our parameter estimates, our estimate of the covariance between positive and negative affect. Again, it's a different model, so it's a little bit off. The way these auxiliary variables work is auxiliary variables are entered in the model and they're allowed to covary with each of the indicators of the latent variable, with the residuals of those. This doesn't actually affect the rest of the model, but it does incorporate, say in this case, great as an auxiliary variable into the model. If we want to do multiple imputation, just to demonstrate how I'm going to use the Amelia package, and I'm only going to do 5 imputations to save time. As a reminder, you should probably do about 20 or 100. The mice package is a nice option as well. So I'm going to use the Amelia function, imputes missing data. I'll use dat4, my MAR missingness, and I'll do 5 imputations, and it's quite fast. In this case, again, I'm not doing any, you'd want to do all your imputation diagnostics and other checks to make sure that your imputations are correct. Now, there are 2 ways we can do this. The first is there are functions called cfa.mi, sem.mi in the SEM tools package where you can specify your model, your data set with missing data, a number of imputations you want. And if you do that, it will impute the data, fit the model, in this case, 5 times separately each data set. And then when we ask for a summary, It should pool the results. We take FMI equals true off of here. I did the wrong thing. I took the wrong thing off. Standardized equals true. I have to take off for standardized parameter estimates. That's right. Hi, everyone. Thanks for bearing with me there. I had a weird issue with Lavon. So we fit a model using CFA.mi that fit it automatically. We can look at the results. The first thing is you won't get fit indices automatically with multiple mutation. As I mentioned, that's an issue to examine that's still under research, but we do get our parameter estimates, so our factor loadings, standard errors. This t-value, degrees of freedom, you can generally ignore this. Technically, the test statistic is a t, not a z, so they're degrees of freedom. You see this inf, that just means they're really large. Essentially, that is the same thing as saying infinity up here, so you can ignore that. But you get associated p-value, standardized parameter estimates, information about the fraction of missing information in each parameter. So if you want to see which parameters are being impacted by missing data, it's available. Same for the covariance. You can see here the covariance and standard error very similar to what we got with FIML, and estimates of variance as well. The other thing we can do is we have this other example fit where we use the imputations we ran, we computed separately. Again, this is generally what I'd recommend. We fit our model 5 times. We can look at our results. They're exactly the same, or pretty close to the same as before. And then we can use the fit measures function to get model fit if you're interested in model fit. So our model chi-square. Here we have CFI 0.984, TLI 0.980, ARM-SEA, and just confidence intervals. And then SRMR down here to get that information. Now, in terms of power analysis, we talked about the Santora and Saris method, where we're doing computing power analysis analytically for parameters. The first bit of this is doing it sort of by hand. We're going to create a matrix. I'm going to call it lambda. So we create a matrix full of zeros with 10 rows and 2 columns, again, because we have 10 indicators and 2 latent variables. So lambda looks like this right now. And then for the first 5 rows, we're going to specify our population value. The first 5 rows, the first latent variable, the first 5 indicators have factor loadings of 0.7. And for the second and 6 through 10, those have indicators of 0.7. So we've created, oh shoot, I just undid it. We've created our lambda matrix here. We can do the same thing with psi, where we create a psi matrix that is has 1s in the diagonal. The variance of each latent variable is 1. Their covariance is 0.235. Theta, I can create one of those where the residual variance is 0.51, and there's no residual covariances. And then based on matrix algebra, we can say lambda times psi times the transpose of lambda plus theta gives us our model implied covariance matrix. I have to give them names to the rows of that model implied covariance matrix, but here we have it. We can fit our model with Lavon, fixing the parameter we're interested in assessing power for at 0, so F1 tilde tilde F2. So we say F1 has factor loadings for V1, 2, 3, 4, and 5 load on F1, V6 through 10 load on F2. And we fit our model with the sample size we're interested in assessing. Here we'll say 250. Look at the model to get the model chi-square. In this case, it's 9.642, and we plug that in here as the non-centrality parameter. So to get power, it's 1 minus p chi-square for 1 degree of freedom. Our critical value at alpha 0.05, 3.84. If we do that, our power to get that is 0.87. What we could do if we wanted, the nice thing is this is fast enough that we could do this. We could compute power for sizes, say 100 to 500, and put that into, so we're doing this 500, we're doing this about 400 times. And then when that's done, we can plot it. We can set up a plot to get a plot of a power curve. That should be just about done. There we go. And so we can plot it if we want, and then we can get let's zoom in on this to make it, oops, it's viewable. So then we can see there's a power curve here. We can see how this is power only for that covariance between the two latent variables, how it increases across sample size. Or we can there's a function called SS power in XemTools for Centaurus RS power. We specify our population model. In this case, so we specify all the population values. F1 loads on V1, 2, 3, 4, and 5. All the factorlings are 0.7. All of these factorlings are 0.7 for F2. Variances of F1 and F2 are 1. Their covariance is 0.235. All the residual variances are 0.51. You have to specify every parameter in here. And then for SS power, we give it the model we want to fit, the sample size we're interested in. Here we'll say 250, so it matches our results up above. The number of parameters that are fixed to 0, and the population model that we've specified here that our covariance matrix should be built off of. And if we do this, we get a value that's exactly the same as what we saw above. And again, we could do this with a different number of people if we wanted, and we would get different power. To use Monte Carlo power analysis, you actually use the same population model that we saw before with all fixed parameters. And we specify an analysis model now with nothing fixed to 0, just the model we want to fit. So here that's going to be F1 and F2 loading on these. The sim function runs our Monte Carlo simulation. We specify the number of replications. I'm actually going to do 1,000. I'm just going to pause the video and come back, and it'll be like nothing happened. The model we're going to use is the model we want to fit is our analysis model, our sample size of interest. Under generate, we specify our population model, the Lavon function we want to use, CFA function, and any other arguments. So let's start this. If we start, the analysis model, I hadn't loaded that in yet. If we start this, we can see it starts a progress board. It starts counting up. As we're nearing the end of our 1,000 replications, just as a reminder, each of these progress that counts is we're generating a data set with a sample size of 120 based on our population model, fitting the analysis model, and saving the results. We do this 1,000 times, and the proportion of those models where a parameter is different from 0, assuming it's not 0 in the population, and here we're going to focus on this parameter here, the proportion of times that it's significant gives us our estimate of power. So we're almost done. And we can see a summary of the results. Now that did not take hours or anything like that. I want to mention there should be a little timing note at the bottom. If not, I'll find the timing here in a second. But so we can see, first of all, down here at the bottom, number of replications and number that converged. We have 1,000, we have 1,000 and 1,000, they all converged. Up here, we have our fit indices, a little information about the average fit index, the first percentile, the first percentile, the fifth percentile of these fit indices. Down here, we have this estimate average. So on average, across all of our replications, what was the average estimate for? Here are the factor loadings, here are the residual variances, and down here at the bottom, we have our parameter of interest, the standard deviation, which is an estimate of the population standard error, and the average standard error. Power is the proportion of times we rejected the null. Here it's 0.593. As a reminder, when we used the analytic method, it was about 0.57. They're very comparable. Our standardized estimate, our average standardized estimate. This average parameter, this is the population parameter here, 0.235. And two of the other things we get from these models, Monte Carlo simulations, is not only do we get an estimate of power up here, this average bias, is there bias in our estimate of the parameter? So are we biased? Are we on average or across all the replications? Are we estimating it too large or too small? The average bias was very small. This is in proportion, but you can think of it as 0.6% bias, which is extremely small. And then coverage is what proportion of time did the confidence interval contain the population value? So here it's 0.935. We want this to be about 0.95. So again, we're doing pretty well, and it looks like our model's working well. All right, well, thanks for bearing with and listening to all that. We will talk about multiple group models next time.